to restart our program. Let me remind you that again, our lunch break is shorter today. We need to come back at 1:45. More importantly, I can now announce that our scientific organizing team is complete. Now Chingwa Kian is arrived. She's going back. So welcome, Chingwa. And then Royce is going to start off the diffusive systems part of this lecture series. Since I was already advertising books, let me advertise his too. Beate and Royce wrote a book 10 years ago or so. 15 already? No, you're lying. So it has accumulated a few years and some dust, but it's still eminently readable. It's highly recommended in this area. Of course, everything that's more up to date, Royce is going to tell you.
Thanks, Uwe. It's always intimidating to follow Sid's beautiful talks. It's hard act to follow.
Could you turn the microphone?
I thought I did. Is it on now?
No.
Is it on now?
There's another switch. Maybe that's the
How about now? Is that better?
Yeah.
Okay.
I got my exercises.
I told you it's a hard act to follow. I mean, Sid already had no problem with this topic. As far as the book that Uber is trying to advertise is concerned, I'm afraid that unless your library has a copy, you can't even buy it on the web because it's out of print. However, we did make copies of our preprint. So if you really want to have copies of it, we'll send you a way of downloading the preprint of the book. We keep talking about writing a second edition, but that's too daunting. Anyway, here's the outline of what the whole series is about, and we started talking about the overview, and we're now going to make a transition into the second part. This is the slide from last time, just saying to you that I've given you a broad outline of what equilibrium statement is about, as far as we're talking, as far as we're concerned. And then we'll talk specifically about Jordan diffusive systems. And in particular, I'm going to be talking about simple models and the insights that they will give, and the many outstanding puzzles that are still around. And as far as the applications are concerned, Jay, Christina, and Steve have already started telling you about real models. And so this is a very balanced place for the organizer. Okay. What are VDS and why do we want to study them? Well, just to take you through the alphabet soup, driven is easy, out of equilibrium, and using different kinds of fields, whether it's direct fields or random fields, or multiple temperature. Now, multiple temperature, of course, is extremely important. You cook every day, and if you want for multiple temperatures, you wouldn't be able to eat, and so on, or at least you eat raw food all the time. Diffusive is easy. It just tells you that the conservation laws are crucial in this particular set of systems. Why do we study them? This is just a review of what we did last time. It's just fundamental issues in non-equilibrium that way. It allows you to get some insight into what's going on. Physics of many systems, in particular fast ionic conductors. This is the set of things that started this entire industry, and I'm going to talk about that. In addition to the physics of systems, there's also systems all around us. And in particular, you have biology, all the way from the micro to the macro level, so we'll be talking about epidemics and what have you. We talked quite a bit about cars already and so on, and there will be many talks about social environments and networks. However, I hope that from the last few talks by especially Christina and Steve and Sid, that you realize that real life is incredibly complex. And so what do you do when you want to discuss something that is very complex and try to understand it? So the idea is that perhaps we can gain some insight through looking at very simple systems like the Ising model. And just a historic reminder, when Lenz proposed this model, Ising, it was considered to be absolutely insane, right? Because you have this hunk of magnet and it does funny things, you're not going to just replace it by two little guys, you must be kidding. But obviously, needless to say, as far as this audience is concerned, we've learned a lot of things about it, and so it's a good idea to talk about simple systems. So simple models and their potential applications. I just want to give you an overall picture of what I'm going to be talking about. So at the beginning, we just want to take the Ising model and just drive it out of equilibrium. So it's just a single species of particles and holes, if you like. So what are the potential? And then you can put in more species if you want. Now, in general, these particles are going to be more than particles. They could be n-dimensional objects embedded in d-dimensional space. And I'll give you a lot of examples as far as the red part is concerned. And then you can talk about different ways of driving them out of equilibrium, how you're going to get different things, and so on. And then you're going to talk about quench disorder, which typically happens in real systems, and on and on and on. It's just endless. So you're saying, hey, wait a minute, are there anything that is not DES? And the thing is that there are many, many other non-equilibrium systems. Sid has already talked about adsorption. If you look at the line, the number of particles is not conserved. It comes and goes, and so on. And then there will be all kinds of other subjects like population, directed population, Bach stands for branching and non-linear random walk, and so on. Epidemics, aging. This is what you'll hear about. So let me then come to DES. As far as n-dimensional objects embedded in d-dimensional space, here just a short list of the things that we can think about. This is the thing that started the whole game, class ionic conductors. Now, what are ionic conductors? Well, you're all familiar with salt. If you take salt and put a couple of electrodes through it, nothing happens. You melt the salt, suddenly current flows, right? So that doesn't make a very nice conductor, and liquid salt is not very nice. On the other hand, there are other substances where the structural property stays the same, the crystals still stay there, but the ions can move within the crystals. Like silver iodine, if I remember. I'm not a chemist, so I hope I remembered it right. In any case, the ions that move from lattice to site as you put the electrodes on. And so you can immediately think of that, hey, I can think of this as an Ising model because where you have the ions there. And now I'm going to take it out of equilibrium by driving it and moving it to see what happens. So that's what started the whole game. And you can imagine those are particles embedded in 3 dimensions. Now the other thing that we have been playing with a lot are models of protein synthesis in which you have messenger RNA, the ribosome comes in one end, walks to the other end, takes off, and it never, or almost never goes backwards, and so it looks like a driven system. And so that's that situation. Now, I want to just talk about one thing which is kind of interesting, because it has to do with physics and so on, is steps on a vicinal surface. Now, what is a vicinal surface? Well, if you take a crystal and cleave it along one of the flat planes, then ideally it would be just completely flat. The vicinal surface is one which is just in the vicinity of being flat, so you just tilt it a tiny little bit like that. Now, if you're tilted a tiny bit like that, what does the surface actually look like? The surface is just going to look like a series of steps like this, right? And there will be a vicinal surface. Now, if you look from on top of this surface, if you look something like this, these are these steps, okay? And now, if you start putting things on here, like absorption and so on, the particles will arrive, wander around here. When it comes to the step, it likes it because it has neighbors and gets absorbed here, okay? After you have enough absorbed guys, then this will advance, like this, right? Okay? So eventually it looks like a bunch of lines being pushed to the right. And that's why it is called one-dimensional object embedded in 2 dimensions. Okay? Now, Steve and Uber has studied quite a lot about flux lines in superconductors. That's easy. Lines that are being driven. Polymer sedimentation is also easy. So polymers, which are one-dimensional objects, which are going down and so on. So you can see the range of things that driven diffusive systems can be tried to. Well, multiple species, that's also easy to think about. You talk about biological motors, multiple uses. We talk quite a bit about cars and different types of cars, and we're going to eventually, the last lecture, the idea of the simple models is to model these traffic jams and pedestrian traffic and so on. So that's the idea of what we're going to talk about this time. Any questions before I get really going? Okay, great. So I'll be shameless and take something out of the talk that I gave last December at the 100th statistical meeting. And the title of that talk is 25 years after KLS. And so you said, oh my God, that's another alphabet soup. What's KLS and why 25 years after? And you have the notes in front of you, so you can see in more detail if you like. KLS stands for cut, equal width, and tone. And the date is 1983, and you can see that we're 25 years through this, approximately, to the time of the Statistical Mechanics Conference. And here's Joe Leibowitz and Herbert Spohn. Cuts, I think, is lab physics or something. I've never met him, so which is unfortunate. But the paper where essentially quite a bit of this seminal work is found is in JSP. This is a PRL, which is comments, which is hardly anything. And as you can see, plasma and conductors was the initial motivation for this entire bit of work. What happened? What happened is that there are lots of surprises and things that you hardly expect for something so simple to give you so many surprises. Some of them are understood, but many are yet to be understood. And you would see this little figure showing up all the time. And that little figure means there's plenty of work for you guys to do. We don't understand what's going on, and you see it over and over and over again in this talk. So, the original KLS. What is the idea? You take a simple interacting many-body system, like the Levy model, that is gas version of it, and drive it far from thermodynamic equilibrium, and ask, does anything new show up? So, here's the well-known equilibrium lattice gas, three-dimensional, unbounded solution applied. Configuration is just the number of occupation number in each slide, whether it's 0 or 1. And here's your energy functional, just nearest neighbor attraction if J is equal to is positive, periodic boundary conditions, fixed total number of particles. That's the diffusive part of the conservation law applies here. So let me just remind you, as if you need reminding, that there's a phase transition for this two-dimensional system below the contact temperature, from the homogeneous to the inhomogeneous pre-separated state. In order the spontaneous ionization, the equivalent of it is either dense or rare, and it would be number dependent and geometry dependent. But the situation is that if you have a square, it would go from homogeneous to either a vertical or a horizontal strip like that. Okay? Now, you know very well that about TC, the correlations became exponentially, and the critical properties are not simple Landau and mean field and so on. So that was static, so now you want to put on dynamics that obeys detail balance. Remember last time we talked about applying rates that obeys this equation. And so the favorite rate is an Metropolis rate when you go on doing Monte Carlo, which is that if the energy is favorable, like this, because when it goes from here to here, it picks up two neighbors, so it likes that, just go. It's rate 1. If it wants to go backwards the other way, it doesn't like it, so it goes with a suppression according to this equation. The 2J is because it lost two neighbors by going back. Okay, now you take this guy and you say, all right, I'm going to drive it far from equilibrium by some additional field. Well, we talked about, for example, polymer sedimentation, so you might want to try to apply a gravitational field to it. So what happens? Well, suppose I turn the interaction off with time being. This means just go, because it's going with gravity, and that means going with rate that is suppressed by the change in the gravitational potential. So you can see what is happening is that we use what is called the local detail balance. So this rate here obeys detail balance, looks like it obeys detail balance. And detail balance, you remember, is a condition that has to do with all possible transitions. So you can't do it by just looking at a piece. So this is what is called local detail balance. Well, we cannot have periodic boundary conditions unless your name is Escher. And you can see that you can just keep going down or up as you like, but we're not like that, so unfortunately we just go into equilibrium. There's an extra potential term. I'm not telling you anything that you don't know already from your STEPNet course. Here comes the other part. If you now apply a quote electric field instead, then periodic boundary condition is possible, because if I put the ions on this piece of paper and I wrap the paper into a periodic boundary condition, I can try to apply a changing magnetic field through here that gives you a E that goes around, right? And therefore, it allows me to have periodic boundary condition. So here, let me just say again, this would be just go because it's happy. That would be go with a rate, and now I just put the J back in. It depends on the E as well as the J and so on. Is that clear what the rates are? Okay. So in this case, you can imagine that eventually, because of the periodic boundary conditions, it would settle into a non-equilibrium steady state situation with a non-trivial particle current. And how do you calculate this particle current? Well, if you had the probability current, you can then easily calculate this thing as an ensemble average and so on. All right, what happens? As you can imagine, when you move in the direction of this along the field, it tends to break the bonds. Okay? On the other hand, if you try to move in the transverse direction, it has nothing to do with the field. It tends to satisfy bonds. Okay? So, does that remind you of this picture? That's why I picked E for this picture, is because originally we were talking about this type of situation. There would be, in general, if you keep track of the changes in the energy to this system, as you move in this direction, it tends to gain energy from the drive and lose energy the other way around. It's no different than if you jump out of an airplane and you sweat like crazy. You're gaining energy from the gravitational field and you're losing it through your environment. Right? I told you I'm talking about simple things. Lots of surprises, one of which is if you go splat on the ground. How does this differ from the equilibrium? One, it violates detail bounds. I just talked to you about local detail bounds. Those rates look like they satisfy R of one divided by R of the other one is equal to either something or another. Now, if you look at it very carefully, it is not the difference of two potential terms because of periodic boundary conditions. If I follow the potential of associated electric field all the way around to the top, I'm going to get some number. It's not going to be back at the same place, right? So it's not potential. Now, how do I see this if I have never heard of potential? In general, this is not very easy to see. In this case, these reversible loops that I was talking about last time is global. It's not local. In other words, if you change the configurations in such a way that it has to do with the entire system rather than some local positions, you will find these reversible loops. All the local loops are reversible. Okay? And so this is part of your homework. That little figure will show up every now and then, so that's to remind you that there's homework to do. Okay, this stationary state goes into non-equilibrium steady state, I told you already about. So, the distribution of this thing is nothing like e to the minus beta h. In particular, if it's a simple homework, you can take a 2x3 lattice, half fill it, that means 3 guys. There are a total of 20 configurations. In the stationary state, there are only 4 state configurations that are not related by translational or reflection symmetry. So you can write down the whole master equation and solve it. Okay, that's why it's a homework. Yes?
So can't you restore global detail balance by artificially creating two states corresponding to the two paths where the energy is flowing into and call them a state?
Yes, if you include the entire, if you include the whole thing.
And I mean, just create
and that's the, and that, right, I mean, if you include these two guys, then you will get them. Okay, but then you're talking about full quantum things. Is that what you meant?
Yeah, but that doesn't make anything simpler because if I just add two states which are artificial.
Okay. So I call these configuration C. Okay. If I call the configurations associated with this path I don't know, curly C, and associate this one with curly E or something. Some other C, some other form of C. Okay, like that. Then the thing that is satisfied heating balance if I write all of them, C, curly C, and this block C. Now what I'm interested in is this one. This is the sum of this. Some of the curly ones and the C. That's what I'm interested in, okay? And if I write a master equation for this thing that obeys detail balance, and I look at the full time dependence, and this is losing all the time, this is gaining all the time, but in a time scale that this hasn't settled into final state, and this has not settled into final state, but this is now final state, so that guy is not satisfied. So it has to do with restriction. And you can't derive the equation for this from this, by the way. It's in general impossible to do. So that's what I mean when I was trying to answer the question at an earlier time, that the master equation that we're looking at is a kind of phenomenological equation, almost phenomenological equation, unlike the Schrödinger equation. Okay? Any other questions? So the next thing I want to show you, this one is a little bit trivial, is the one which is slightly more complicated, the 2x4 lattice. And you have the picture in front of you. And there are 70 configurations total. 12 of them are not related by symmetries. And here are all the 12 that are not related by symmetries sitting at the bottom of that list. And what you're looking at is the equilibrium distribution. This is nothing but E0 minus beta H. That's easy to do. This is done by maximum drive. What do I mean by maximum drive? If the E is so big that it overcomes all the broken bonds and so on, and it never goes backwards. So for example, to go from here to here, this line comes down with rate 1, and it never goes backwards. This one never goes downward. So these W's are 1, and those W's are 0. That's what is meant by maximum drive. By the way, this one, to go from here to here, is just the usual Boltzmann factor. It has broken 2 bonds, so it's going to be suppressed. Okay? There's no drive associated with it. This one, you can write down the master equation, you can solve it, and here's what it looks like. You can see that the Boltzmann distribution in this one is very, very different. In particular, the most probable state in equilibrium is just this one. Why? Because it has the least number of broken bonds. Right? So it's happiest. So that's this one. By the way, the largest P has been normalized to 1, so these are relative probabilities. It's way up there. Meanwhile, the most probable one with the maximum drive case is this one. And if you look at this distribution at very high temperatures, you see that I have no idea how to go from one to the other in terms of intuition. So I don't know what the intuitive picture of this guy is. It's not just E0 minus beta H.
Are you driving them downwards?
Yeah. In essentially all these lectures, the graph is vertical. Okay. Fluctuation response relation, you remember that one of the things you have to do as the first time studying setback is that the specific heat, the behavior of the internal energy has something to do with the energy fluctuations. In fact, they're supposed to equal each other. That's very easy to do. But in this even 2x3 case, which you're supposed to do as an exercise, you see that the specific heat goes up and comes down, has a peak at some funny value, and then the other one is monotonic all the time. So it's violated all the time. That's a little bit of homework to do. There are many surprises. And the list of them are what this whole lecture is about. Incidentally, you should not be surprised in the presence of anisotropy. After all, the drive picks up the direction. So that's not the case. The surprises come from when the breakdown of well-founded intuition from equilibrium step back. So let's begin with the simplest thing. In equilibrium, Ising model, you know something about the fact that there's an order state, there's a disorder state, and there's a phase transition. Then the KLS is just going through the drugs. What is your bet? Does it stay the same? Does it go down and saturate somewhere? Does it go down and then vanish somewhere? Does it go down immediately and then go somewhere? It's hard to imagine that it would go up indefinitely. It's hard to imagine it would go up right away. Remember, this is the order state, that's the disorder state. Okay? All right, what is your bet? I know that physicists are not betting people. So, who bets on this one? This is the transition, this is the temperature, this is the drive, this is the ordinary angular. As you raise the temperature, it goes from an order state to a disorder state. If you now drive it, would it stay the same? So it's just order here and disorder there. Would it go up? Would it come down? Would it do this? Would it do that? Or what? What is your bet? Okay? So, I don't have any clickers, so I'm just going to ask you to raise your hand. Those who know the answer, since there are many people in this audience who know the answer, I'm not allowed to vote. So, who wants to vote for this one? How many votes? None. How many votes for this one? One. Very few. How many votes for this one? A few more. Wow, quite a lot. Fantastic. About maybe 1/3 or so. How many would vote for this one? Nobody believes that the drive is no different. How many would vote for that one? Go on, a handful. You don't count, you know already. I'm talking to you, right? I see that a number of you didn't vote, or didn't bet, and so you guys are probably too young to know a story, which is that the APS meeting was once held in Las Vegas, and all the physicists were hovering around a table watching what is happening, like all good physicists. They want to know what's going on before they bet. And so Las Vegas lost a lot of money. And they said to APS, you are never welcome back ever again. But if I remember by just looking at the audience, most of the people spoke for this one. So, I'll give you the story. This was my first guess when, in fact, I was visiting Herbert Spohn in Munich, and he was just looking at this stuff, and he told me about it, and I said, wait a minute, so what if there's a current? Why can't you just go into a co-moving frame, and the whole thing should be just an Ising model? And I said, no, it doesn't go like that. It doesn't go like that. Well, I gave up, and I didn't work on it anymore, and regretted that decision. In any case, I saw that a lot of people voted for this one, and that is precisely what you would guess, based on equilibrium intuition. Why? You remember that when you drive a system, you are essentially pumping more energy into it, right? Pumping more noise into it. So you imagine that you are making the system more disordered. So if you go from here to here, by adding the drive, you will imagine you are making more disorder, and if that is the intuition you're using, great. GC goes up. So those of you who voted for that one happen to be correct in this case. So what happened? Well, what happened is that the internal energy goes down, and the system actually orders in high temperatures. How in the world did that happen? And before I do that, let me just tell you that DC can also go down depending on the microscopic dynamics. It tells you how badly off we are. Most of the people who are doing, large-scale Monte Carlo simulations for equilibrium Ising models like critical exponents, they're asking for the third digit, fourth digit, just like that. We don't even know the sign. We don't know the first digit, we don't know the sign half the time. What is going on later? So, let me just show you a little bit of what the typical configurations look like. Here's the equilibrium Ising model. It's slightly about PC. The guys are trying to gather and trying to order. You have a large sort of cluster that is doing that. If you drive it, just come to 1.1 PC but a very large E, you can see now that this patch has order. Okay? There's a high density state and a low density state there. If you, that is to say, somehow drive induces order in this entire system. If you were to crank up the temperature, it indeed goes disorder again. Now, this is coming back later about worse. The details depend on the microscopic. If you make sure the drive goes along one axis, it did that. That's what you saw. If on the other hand, if you take the g hat component along the other axis, it goes back. This little bit we at least have an idea of now how to understand. What is really puzzling is that this qualitative behavior doesn't depend on whether the drive is direct drive like this, periodic ones. In other words, you can try to reduce it from AC if you want, or random, where you just do it at random, and so on. But why are they the same? We don't know that. Let me just make a short tutorial what they mean by AC, that's easy, in the form drive, and the random drive. Later on, I'll use these two colors to denote either random. Random in time and not random in space, and random in both space and time. Okay? Now, if you take a field and drive it in random space and time all over the place, then that is what is sometimes we call the two-temperature model, because if you were to do the following with the rates instead of the ones that I'm talking about, I'm going to tell you what the rates are. You take a guy and you try to move it this way or move it this way. You try to move it this way, you use the same metropolis rates that you've done before, except with a higher temperature, with a smaller beta, higher temperature. So this way you just have beta, say this way you have 0. So 0 means what? 0 means just move it. Don't worry about your neighborhood, okay? Just move the particle. Random walk in this direction. That is equivalent to t equals infinity, right? That's what you mean by t equals infinity. It's just do random walk. So if you do random walk in this direction, and then that way you update according to the right things, you will get to the same kind of curve. It just goes up like this. It's just, we still don't really understand what is happening. So this thing, and you talk about these sort of things. So one of the things that we begin to understand is the idea of negative response. The E adds noise, it looks like a high temperature, but nevertheless you have order. Now, it turns out that Gene Stanley, who is very good in picking the right words, calls this phenomenon freezing by heating. So the idea is you go to the wall, you turn off the thermostat, and you freeze. Okay, the negative response is meant by that. The internal energy of a system can go down when you take one of the thermostats and crank it up. Equilibrium, that never happens. So these friends of mine, one of them has done some simulations or something and once wrote me and said, I'm getting negative specific heat, should I worry? And I said, what are you doing on equilibrium, why should you worry? And he says, well, you're a good friend, I trust what you tell me, but can you show me that I shouldn't worry? So I scratched my head a little bit and I finally come up with something so simple that we decided to publish it in the American Journal of Physics. That's perfectly readable. It's about 2x3 systems and things like that, and that's why I call it getting more by pushing less. This is all about negative response, and you can read all about it. Okay, that's negative response. The other thing we begin to realize about these driven lattice systems is that the correlations, no matter how far away from Tc, except that T equals infinity, is that it is long range, power loss. Just to remind you, in equilibrium, it's exponential ahead, okay, about Tc with some correlation there. Now, the amplitude in front of this, just in case you're worried about the integral of this thing being divergent, the amplitude of this does depend on the direction, and if you integrate over the angles first, that goes away. You say, where does this r to the minus d come from? And this argument is beautifully given by Jeff Bernstein some time ago, and it rarely appears in the literature. And it's so easy that I can just reduce it here for you. So consider the correlation function at a distance and a time, okay? And now you know that g of 0t, because of the conserved system, goes like e to the minus d infinity. This is just the simple thing about integrals. You integrate over r to d into. So the other question that we are interested in is you take the same operative upon equal time correlation. Okay? Now, if you remember scaling it off, about Tc is just diffusion, that is dictating thing. And diffusion means all should scale like t to the minus 1/2, t to the 1/2, right? This is diffusion. If you know about scaling, and you know this, what is the conclusion here? Optional minus t, right? So you say, good heavens, what happened in equilibrium? Why is it e to the minus r over psi? Where does this come from? So it turns out that this is generic. Equilibrium is the really unusual thing. What happens is that this amplitude that sits in front is always non-zero unless you go to equilibrium where fluctuation dissipation theorem forces the star to be zero, and that emerges. So it's really quite amazing. Yes?
Yeah, but why can't you... But that is a still invariant form anyway, right? E to the minus r by psi. No, I mean,
This one, from here.
No, the right-hand part.
This one? That one?
No, the one.
This one?
So why couldn't I just have r to the power minus e to the power minus r by psi as a function?
You don't get from here to here by scaling arguments, right?
No, I agree. I get from here to there, but my whole scaling function can very well be 1 by r to the power b and a function which is scale invariant, right? Which is what the exponential function is.
Maybe I'm not understanding you correctly, but the typical statement about scaling is that if you go to one edge of the scaling function and it has a certain behavior, and you know the relative scaling of R. So the idea is that if you're...
I'm arguing about the a going to 0. Why is a has to be 0 that I didn't get?
Oh, this is something that one has to show. It's not particularly easy. What I'm saying is that the amplitude that sits in front turns out to depend on the violation of fluctuation dissipation, which has to do with non-equilibrium. So equilibrium is the unusual part. This is still equilibrium. This is still equilibrium. Okay, and that is still equilibrium. I don't know whether I answer your question or not, but if scaling is what your question is, then if a typical scaling function that you are talking about x to the power and some scaling function of x to another power and y to is what when it comes to these two things. And so if you know the scaling function there, you use this argument, you will come here, not the other one. What is it related to? Related to another very strange thing is that there is discontinuity singularity in the structure factor. What is the structure factor? It's nothing but the Fourier transform of the correlation function. Experimentalists use this all the time because you shine a beam into the system and you look at what the pattern of the scattering is at, and that's exactly what you see with this thing. It's easy to measure. Now, let me remind you that if you apply Lorentzian criticality, then this guy is the Lorentzian form, it's just a Lorentzian, 1 over k squared plus a constant, that constant is the correlation function squared. If you plot this guy, you would just see something that looks like this. If I call this the amplitude of it. Okay? In other words, if you shine a light, is this thing working at all?
It is.
If you shine a light through a beam, a substance, you know that there's a fuzzy patch, but it's bright in the middle and dim in the back. That is this. That's all it is. Now, so that was a homework that this thing has to do with exponential correlation function. So here's we made these things for a long time ago, so we didn't have this nice PowerPoint and so on. So this is a contour plot of a structure factor. If you take an Ising model with anisotropic interaction, stronger this way and weaker that way, or what have you, the bright spot will be in the middle, but it will be elliptical instead, like that. But if you drive the system, suddenly it will have an owl shape like this, and this owl shape thing has the following situation. If you come from this direction versus you come from that direction, you go to different levels. Okay, that is what is meant by discontinuity singularity. So if you put kx equal to 0 first, and then coming on the ky direction, you're coming along here, and you see you cross very few contours. Very nice way in the mountains, because people can understand contours. If you're coming this way, you can cross a couple of contours. If you set y equal to 0 and come in on the kx, you can see you come through many more contours. And there's a sharp discontinuity in the middle. When you Fourier transform discontinuity, this is what you get. Okay? So, this is a little bit of a big jump. for people who are not familiar with the Convergence equation, what you can do to get to describe this kind of structure factor is to then go over the density. Like in the Ising model with conserved dynamics, what do? Well, you take the density and you say how does it depend on a function of time if you want to do time dependence. But before you do time dependence, you start to look at the gradients and what have you. This is sort of that's the sort of equation that Christina was talking about. So the Convergence equation is really an equation that has the time-dependent version of that Ising model. And you add noise, and then you modify a little bit and add heat. It would lead to the following structure. The structure factor, instead of being 1 over k squared plus a constant, has k squares on top, has k squares on the bottom, has k to the fourth on the bottom, as well. And then there are various coefficients. And what fluctuation dissipation does is to force the relationship between the noise correlations, that's what these things are, and these coefficients, which have to do with the dissipation, but to have a certain ratio. And if the fluctuation dissipation is not there, then this number here, which has to do with the sigma parallel divided by co-parallel, divided by the other way around, sigma per divided by co-parallel. Okay? So that is your R. Oh. So the density we've been talking about, which is a function of x and t, okay? And instead of using the density, we're going to talk about the magnetization, which is just equal to, let's see, this is 1 minus 2 rho. 1 minus 2 rho. When rho is equal to 1, it's 1, 2 rho. What's that? When rho is equal to 0, it's minus 1. When rho is minus. There are certain things you should do in public, and there are certain things you should do in private. As Sid has pointed out very well. Use this thing that the Hamiltonian for phi would be something like the usual gradient phi squared, 1/2 plus tau times phi squared plus u times phi 4. Are you familiar with that? Great. So then PDT of phi is equal to, and now the Convergence equation is nothing but saying this is delta J, and then plus noise. The noise part is the one that is non-Convergence equation, and this is like Christina was talking about yesterday, the gradient of mu, and the mu is dh phi. Okay? So eventually you wind up with something that looks like this, del squared of phi squared, and gradient squared phi plus mu by 5 squared. So 5 by 3 to the 4 over here is the dish. That's plus 1. So that's the Convergence equation. So the only difference between this thing and the usual situation where the dynamics is non-concerned with the gradient square is missing. Okay?
So this is
this is what, yeah, this is the equilibrium. Very good, very good. So for non-equilibrium, you need to add the drive. So for non-equilibrium, then you say, how do I add the drive? Well, we've seen this equation before. And we're going to add this in there. If you let sigma be constant, then it just disappears from the continuous. Because if you let sigma be constant, you let del dot j is gone. Right? E is a constant, remember? So the thing to recognize is that when you write something down like this for the freshman physics, you should try to remind them that sigma is not a constant, it's not density independent. In particular, this is something I like to treat freshmen out, is that you also need this equation. And so if you equate these things, then you get the velocity is equal to sigma divided by rho e, which means as the density goes to 0, the velocity goes to infinity. Something is fishy, right? So anyway, the idea is that this sigma must vanish. There should be no current if there are no particles. And because we're looking at a situation with excluded volume, if the density is full, there should also be no current. So sigma has to be equal to 0 if rho is equal to 0 or rho is equal to 1. So this is a condition for the kind of current that we're talking about. So we substitute in here, the simplest thing that satisfies the condition, which is rho times 1 minus rho, which is of course equal to 1/4 times n minus phi squared. Just put that in. And now if you take this guy and plug it in, then there will be an extra term. So that's what happens.
It's just a linear equation.
Yes, yes, yes.
It's an equation that is
Correct. It's a logical equation.
it's an equation that you need to supply in addition to the it's an equation of motion that you need to supply to the Ising system in addition to
If you want to describe the dynamics.
Dynamics.
Correct. You take equilibrium Ising model and you give it different types of dynamics and add the noise, and the noise on the equations, and they go by the names of model A, model B, model C, blah, 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 blah. It keeps going on like that. So this is model B for the ones who are familiar with this entire system. It's the Ising model with the conserved dynamics. The modification is adding this one. Now, there's quite a bit of work to go from what I've just said to this thing. And let me go on and talk about the surprises. And if you want me to talk about the details.
And you're also talking about an anisotropic version, given that you have sigma and tau parallel.
That's right. Yes.
So, real quick, because I missed it.
Okay.
Can you tell me physically what are tau? Sigma is the conductivity, and tau is the.
Okay. So in the equilibrium Ising model, right, the tau that is sitting here has to do with the when tau goes to 0 is where the critical point occurs, because if you forget the gradient terms for the time being, then tau positive, the potential will look like that. Tau equals to 0, the potential will be very flat, and when tau is negative, you would have the possibility of phase transition. Okay? So tau is a measure of how far you are from criticality. If you start from the microscopic Hamiltonian and you try to get here, the answer is not easy. Okay. You get to this kind of form. This is what is called a Landau. This is a Landau Hamiltonian. This is called a Landau-Ginzburg piece, which adds the fact that you're near sensible. You can take mean field theory and you get these specific values for these things. There was another question. Yes.
I'm a bit confused. So you have a diffusing. So there is a bias in one direction, right?
Yes.
There's no reason. I mean, why can't I why do I have to have this phenomenological equation? Why can't I use that to modify my diffusivity directly in the Landau-Ginzburg equation?
In what sense?
So I can have a.
You mean a linear term?
Yeah, I can have a linear ingredient term.
Yeah, that you can get rid of by the linear integration.
But there is no symmetry that's telling me that a single gradient will be absolute.
There is a symmetry that tells you about this because particles go this way and holes go that way.
But there
That's
is
what
bias.
this is. Particles goes one way and holes goes the other way.
But there is a bias, right?
Yes?
And that's bringing a symmetry of.
Correct, absolutely. So look at this term. This has the Ising symmetry on phi.
Exactly.
When I put phi squared in here, it destroys the Ising symmetry. Sorry. So I would add a term, add or subtract a term that looks like this phi squared. Does that help? Yeah. The square here. And that's what this
everything in there. I think the question is everything in this first line, the line above becomes anisotropic.
Oh no, you weren't asking about anisotropy, you were asking about bias.
Yeah, I was asking about.
He was asking about the whole particle whole symmetry.
Yeah.
It also becomes anisotropic, but that's a different story.
You also may want to say that those sigmas are not that sigma.
I'm sorry.
Those sigmas are noise correlations.
Yeah, this is not the conductivity. Okay, yeah.
There is a fundamental thing I don't understand. Since now you consider the non-equilibrium system, why you can still assume a global temperature for the system?
I didn't assume a global temperature.
But the temperature is
where
for the whole system.
what did I say that made you think that? So maybe I should rephrase it. So where did you think there's a global temperature? The T?
Yeah, the T.
In the rate? Okay, that T is not the global temperature. No, there's no temperature in the usual sense when you go to equilibrium. That so-called temperature is the thermostat that controls the jump sideways. That temperature is the T of this T. So I keep showing this picture. There's a heat here and that T here. It's that T. It's not the whole thing. So in here, I have no idea what T is. I don't even know what T means. You see, if you remember, where does T come from in the equilibrium statistical mechanics? It comes from the fact that I take the isolated system, okay, and then I say, oh, I'm going to put another system next to it and let them exchange. So where do they then stop exchanging? And the answer is a particular thing, namely if you set DSDE here equal to DSDE there, they would stop. And you say, oh, this is exactly what I see in my real life. I take this object, I take that object, I put them together, and they would eventually come to the same temperature. I should identify that object with the temperature, right? One of the problems we face constantly, I take a system that is non-equilibrium, take another system that is non-equilibrium, put them together, what happens? I don't know. In general, we don't know. One of the major questions that face us is even the Zeroth law. If I take one non-equilibrium system and another non-equilibrium system and put them together and let them come to some kind of stopping exchange, take a third one and do it again with this one and that one, come to that's lots of things are really unclear. And it depends on how you do the exchange as well. Any other questions? Okay, so we talked about the singularity, this whole business of long-range correlation related to another crazy phenomenon, that is that ordinarily, if you take a big Ising model and you take a little window in it and say, what is the average number of particles in there? 1/2, which would half fill it. What are the fluctuations? Some number or another. If you take the window and do this, is it going to change? No. You do this, it changes. Okay? So life is really quite difficult. Okay, as you go to RTC, you better go some distance. We end at noon, right? What time do we end?
Including the question sessions.
Wow, I better go if we want to see some beautiful pictures. So, as you go to RTC, typically the structure factor divergence. That's critical in lessons. But there are three possible scenarios for this divergence because the S have a discontinuity. So what happens is that the simulation showed that only the first possibility happens, namely that R goes to 0. R is the ratio of these two approaches, and that implies the following. Okay, that you have anisotropic scaling when you go toward near the TC. What does that mean? That means that the momentum in the length scales in the drive direction and the length scales in the perpendicular direction don't scale with equal to 1. So the delta is not equal to 0 here. And as a result of that, new universality classes show up, and worse than that is the fact that the critical dimension is not the same as equilibrium. Because of course, in equilibrium it becomes 5 for the uniformly driven case. For the randomly driven case is 3. So although TC looks somewhat the same, the critical properties are not the same. The fixed point there violates the detail balance. It is a truly non-equilibrium system. And the one that is randomly driven is then somehow taken back to a detail balance type situation. So the randomly driven system actually looks like an equilibrium system. Yes?
So randomly driven, there is a local electric field which is random? Is that what
yes.
I missed something?
Yeah.
Okay.
Yeah. Think of it as locally, every time you take the step, you pick the electric field to be pointing up or down.
Okay.
And it's equivalent to what we call two-temperature model, which is, think of the fact that you pick the particle and you want to jump this way, if there's a hole, just go. Okay? Yeah.
For these results on the randomly driven electric field, would the results on the randomly driven electric field be a particular distribution in mind, or is this for different distributions?
You mean the P star? You mean that distribution? Or what distribution of the randomness?
Yeah.
Flat would do, anything would do, Gaussian would do. They more or less give the same results. At least as far as our food simulation shows. Nobody has studied it in detail. Yeah.
I'm sorry, DC is what I'm from last. This is the critical dimension for what?
Okay. Are you familiar with the equilibrium DC?
Yes. Yeah.
So this is the upper critical dimension
Okay.
below which the medium theory lies.
So this can you probably guess by Harris criteria or something? No.
Not that I'm aware of. No, Irish criteria. So lots and lots of interesting things happen there, still a controversy. Let me go to below TT briefly, because there's where all the really surprising things happen. What happens in equilibrium? When you go below TC, there's phase separation, there's coexistence, and there's an interface between them. Inside the ball, nothing much interesting happens. You have Gaussian fluctuations and so on and so forth. But the interface is a Boston mode, is a soft mode. You can push it around, and you see it all the time because you can watch the fluctuations of the interface between the water and the gas. Fluctuations inside the water you don't see, right? So a capillary wave, and if you do the Ising model, interfaces like that are different than interfaces like that because of the lying square lattice. The surprise they bring is that the interfacial properties becomes completely horrible. The SRQ is the same as the Fourier transform of the height-height correlation. Think of an interface like that, H stands for the height. Height-height correlation function. In equilibrium, because it's a Gaussian mode, it's just 1 over Q squared. But when we do the simulations, we get 0.67, and then for the randomly driven system, it's like that. We have no idea how to get this. We get a theory that predicts 1 over Q, but we miss the C. There's a gap in the structure factor, and it's just totally not understood at this stage. So, because of the structure factor is like that, the interface does not diverge with L. In equilibrium, this is a random walk situation. This is because that is time, the width is like the space, so space goes like time to the 1/2. Worse than that is in equilibrium. You talk about surface tension, you can associate the free energy with the interface. With this system, we have no idea what the free energy is. So the meaning of surface tension becomes completely unclear. As a result of all this business, there are new order states that happen if you were to shift the boundary conditions to different ones. Let me remind you, if you take the equilibrium phenomenon and do shifted periodic boundary conditions, in other words, instead of this point being a neighbor of that point, this point being a neighbor of that point, the interface you induce is at an angle, right? The thing would be at an angle like this, and you would then be able to calculate the anisotropic surface tension in this one. Similarly, if it is open, then of course the surface is very different, and you would have some kind of boundary layer to talk about. What happens when you drive it? Well, here's what is meant by shifted periodic boundary conditions. So you come out that way, you come that way. The whole strip tilts a little bit, and you can imagine that, or you can try to understand what's going on. However, when you were to shift it a little bit higher, then suddenly you have multiple strip configurations. This is going from 1 to 20. So this looks like a multiple strip configuration, except that it really isn't. It's actually a single strip mode with wound. In other words, this guy ties to this guy, ties to this guy, ties to this guy. Yeah.
Actually, I don't understand why there is a slant.
Because this is the nearest neighbor of that one. That's what shifted periodic boundary condition means. Okay? In equilibrium, this would be just something like that.
This is just an artifact of your type of boundary condition.
Yes, it's an artifact in the sense of a simple model, but in equilibrium, this is precisely what you do, is find an interface that is tilted relative to the axis, and therefore you can compute the anisotropic surface tension. The surface energy, the free energy associated with an interface that is tilted at an angle. How do you get it by methodology? How do you find it? This is how you do it. You put a shift on it, and then it induces an interface on an angle. I mean, calculate. If you want to do it theoretically, you can try to calculate the free energy of the entire system, subtract it from the bulk, and you will get the remainder, and that will depend on the angle. Okay?
So for the non-equilibrium strike here, the strike rate.
That's right. That's right. Actually, there's something going on here as well, but I'm not going to go into details of that. Let me continue a little bit, right? So we don't really understand that. When does this transition occur from one to multi-strip? And what is its nature? Well, one of my students who never published his thesis started to look at this, and if you look at a shift of 6 up there of a system that is 72 by 36, you can see that one of the interfaces is starting to do something a little bit different. Let me put it together like this for you. That's what it looks like when I just duplicated it. I just took that little guy and duplicated it all in place so you can see what's going on. One of the interfaces is still tilted and still has the structure, but the other one is starting to go. Okay? How does it go? How does it do that? It hasn't been explored. Let me turn it open. I put guys in the top, now I take guys out of the bottom. What happens? You get icicles. They don't get strips. Worse than that is that if I make the system twice as long, I go from 8 icicles to 4 icicles. What happens if I make this thing really long? If I double it again, I got 2 icicles. If I double it again, I get 1 icicle. If I double it again, what happens? Any guesses?
1 icicle.
Stays 1 icicle?
You get back into
Huh? You get back No, if I make it really long. Well, let me tell you the answer. When you do simulate it, if you take a system that is incredibly long and thin like this, you get a single icicle in the middle. The angle stays the same. The angle seems to be controlled by the microscope. The position of the icicle can shift back and forth. That's what happens when it's really long and thin. Do we know how to calculate it? No. We don't even have a hand-waving argument like the good ones that Sid has shown, on the back of the envelope. How to get a hold of this angle? No idea. Even worse than that is, we know that if you take an Ising model, equilibrium Ising model, we know they will look like this. Because it likes to make less and less interface. Right? This is the smallest interface it will make. As you lower the drive, this is for infinite drive, that's what I've shown you. As you lower the drive, you would imagine that this thing would get shallower and shallower before that. It's the opposite. It's longer and longer and longer. It's really incomprehensible. And the last thing that happens is discontinuous.
So how much of these would be dependent on lattice that you use if you use a hexagonal?
Oh, I'm sure that it depends on the lattice. If you take the drive at an angle, it's already going to be completely different. Remember, TC goes up, this is down. Even the sign changes there already. Remember how simple this model is, right? So, let me just show you one more thing before going into question and answer. So you know that in the equilibrium Ising model, if you're below TC, you start well for a random situation, you would try to coarsen and we try to make this strip somehow. You try to make bigger. That's where conjugate was done to begin with. So if you start to do this with a driven system with a lattice, instead of icicles, you have inverted icicles. See, they're pointing upwards. Literally, these guys are going down. I call this the toe plaza effect because you've gone, by the way, E is not infinity, E is 27 at the moment. You've gone into toes, and you notice that somehow the end ones are always a bit shorter in the middle of the figure. So this is kind of like cars coming in, and they like to pile up in the middle rather than edge. If you are going to try to do this with the trihydrate equation, the one we were talking about before, that work beautifully for equilibrium, everything works beautifully for equilibrium, you get the opposite. So you get icicles. We can modify the rules of the driven lattice gas to get icicles, so we can modify this so we can get these, but we don't know how to modify the trihydrate to get toe plazas. lots and lots of work to be done. There's no simple scaling. There is transfer and longitudinal exponents differ, and everything is just really incredible. Let me just, there are lots of other things as well. I can put in anisotropic interactions. I'll just briefly say one thing, because just because Ria is here, if you want to hear about all the strange things that happen to anisotropic interactions, we can talk over lunch, because again, things are really strange and so on. Let me just try to rush through this, because I noticed that we all want to go to lunch. So, what happens? We really need a new paradigm, because all the intuitions that tell us what to expect is somehow gone. One of the ways possible forward is to study Alex systems, obviously. And so, how about we go to a simpler version? I'm reminded of a wonderful lecture by a topologist. It was a public lecture. And he was trying to say how ridiculous it is to have these intelligence tests. You know, you have a sequence that is 1, 2, 4, 8, 16. What is the next one? You're supposed to answer 32, of course. And so he says, well, you know, consider the number of regular solids in 3 dimensions. There are 5 of them. How many there are in 4 dimensions? Well, it's hard to do. It's hard to calculate. Perhaps you can go down 1 dimension and ask the same question, and you can use this rule. Okay? So in 3 dimensions, you have 5 of these regular solids. In 2 dimensions, you know what the number here is? It says, well, infinity is static band. Maybe it's a similar point. Let's go down 1. It's easy. That one is only 1 regular solid. You go down 1 more. Point is pretty regular. So what is the next one? So this doesn't always work, but perhaps we should try. Go down in 1 dimension and see what happens. How about going to the same thing? Do what Mr. Ising did. He couldn't solve the 2-dimensional model, so he tried to go down and look at the 1-dimensional model. Well, so we went to go down in 1 dimension, and you lose an isotropy. Stationary distribution is now still not known. Nobody knows that. Unlike Mr. Ising, we can't calculate this. There's no order space like the Ising situation. There are no non-trivial states. There are non-trivial states that show up if we now start putting open boundary conditions. How about if we look at an even simpler situation? Set all the interactions equal to 0. Okay. And that is the subject of the next talk. Bare bones. As little as you can possibly get. So, any questions? Yes.
So what's the technology that you use here? Just basically continual equation with the workforce, or simulation? Do you have proper conditions? How do you approach it?
The way that we explore things is the first one. And then we try to somehow build a model. We can't solve the math. We try to put it in context of equation. And what is really bothering us right now is that most of the time, it gives you motion. And we don't know how to modify it in such a way that it gives you something that is normal. And that is the idea, how little we understand non-equilibrium. Because if you understand non-equilibrium, if you understand equilibrium, you can start to build these models. And they go to the thought. Yeah.
Why is it the fact that if E goes continuously to 0 that we're not coming back to the...
We can't calculate it. We have no intuition. I mean, I can wave my hands, but the trouble is, I can wave my hands this way and get one answer, wave my hands and that is what makes this whole subject interesting, because it's so simple. You think you know what's going on. You go like this, you get one answer. You go like this, you get a different answer. Yeah.
So you say you could modify your rule-based model to get the continuous
Yes.
form.
Yes.
How do you? What's the
Well, let it jump sideways. Those are the little things that we understand. Those are like the negative response we understand, like the long-range correlations we understand. We understand how to get the isotope. But to understand the microscopic what to do with the dot?
Just make it sideways.
Diagonally set. So in other words, give it instead of saying that if there's a particle here, it can't go down, also let it go down. Yes.
So in equilibrium stat mech, the idea is you calculate the partition function and you know everything. Is there something analogous that, maybe it's very difficult to calculate, but if you could calculate it, you know everything about the model and everything comes out?
That's what I'm hoping that you guys will tell us. I mean, we have a master equation that says if you were to simulate this system, the master equation is well defined. All the rates are sitting in exactly how you program the computer. Then the question is, how do you then tell me what the thing is going to show up? And we don't have any intuition, no, not any. We have some intuition, not zero, but it's so limited, we can't get these things. Yeah.
Where does the co-moving frame argument go wrong?
Oh, very interesting. Yeah. I never appreciated that when you couple something to a thermal bath, you violate, you break Galilean invariance. The thermal bath knows what frame you're in. So that's what happened. Good. People are hungry.
Well, let's go to 1:45.